Hello guys, today we are starting a new topic.
Wait! I haven't told you what it is yet.
Which is network models. By network models, I mean the problems that are defined on networks, or maybe it is better to say on graphs. To be more specific, we will study three very famous and popular problems of graph theory, namely the shortest path problem, the minimum spanning tree problem, and the maximum flow problem. So let me write them down over here. First, we will talk about the shortest path problem. The next problem will be the minimum spanning tree, and the last one will be maximum flow problem. I will give you a precise definition for either of them, and I will give you an algorithm that solves the corresponding problem. But before that, we have to start with some preliminaries. I will define a graph, and I will give you some introduction, some background, and I will define some terms so you can easily understand each problem and its objective. Okay? As I said, all these problems are defined on graphs. So the first thing is, what is a graph? You are all familiar with this concept, so very easy and simple concept. A graph is a mathematical object of this form. So you have a set of nodes, these things, and these nodes that we also call vertices. These nodes are connected to each other with some links. For example, these and these. This is an example, a very simple example of a graph. Okay, this mathematical object is a very powerful tool. Why? Because many real-life systems can be easily modeled using graphs. Okay, a graph is a tool to model decentralized systems. So when you have a system, that the best way to represent that system is by some mutual connections, then you can easily form a graph about that system. You can easily model that system in form of a graph. Okay, so more formally, a graph G is usually represented by the set of its vertices and set of its edges. So V is the set of nodes, also called vertices, which is a plural for vertex, and the set of links or edges. I prefer to use these two, edge and vertex. So from now on, every time that I say a vertex, I am referring to these objects, and every time that I say an edge, I am referring to the links. Okay? As I said, graphs are very powerful models, and in real life there are numerous examples of systems that are modeled using graphs. These are a few examples. For example, you can easily imagine that a graph can easily capture a social network, the content of a social network. Look at here, for example. This is an actual network of tweets. So every vertex represents a person, and these links between them shows the relation between these two persons. Okay? For example, they are following each other, or something like that. Generally, in a social network, it's a very common application of graphs and network, a social network. Every person is represented by a vertex, and if two persons are in a relationship, for example, if they are friends of one another, then we put a link in here, something like this. So In the context of social network analysis, this graph means that this person is friend with all the others, but these two are not a friend of one another. Okay? The other examples include, for example, in a computational biology, a very, very famous graph in computational biology is called PPI, or protein-protein interaction, in which every vertex represents a protein, and so you have two proteins, and these two are connected by an edge if some sort of biochemical reaction is known to exist between them. And these are examples of real-life PPI graphs. Here, here, and here. Okay. Another example is in the field of business. In here, you see a graph in which every vertex represents a company, and the edges show the connection between these companies. As you can see in here, some edges are thicker than the others, which probably means that the sort of business that they have with each other is stronger, or maybe a more cash flow. For example, in here, in between Google and Yahoo, you see a thick edge, which probably represents a more familiarity of these two vertices, or a stronger business between these two. So this is another example, and as I said, there are numerous examples in real life in which we are dealing with graphs and the problems that are defined on graphs. With this introduction, let's go forward and let me introduce to you some terminology in the field of graph theory. A graph is called an undirected graph if the edges are undirected. Okay? So in the next page, you will see that the other category is directed graphs, in which case every edge has a direction. Okay, like this. But when we talk about undirected graphs, there is no direction associated with edges, which, if you think of it as a network of a transportation network, for example, it means that it is possible to go from 1 to 2 by this edge, also from 2 to 1. Okay, so either in the context of the actual problem, it doesn't matter, that the direction doesn't matter at all, or every edge is actually bidirectional. In those cases, we use undirected graphs. Okay, so every undirected graph can be transformed to a directed graph by just putting two arrows like this at the end of every edge. As I said, the other category is directed graph, which we also call it D-graph. And intuitively, a directed graph is a graph in which every edge has a direction. Okay? In this graph, for example, it is possible to go from 6 to 1, but it is not possible to come back directly from 1 to 6. But if you want, actually, I don't see a path from 1 to 6. So in this graph, it is not. I will introduce the concept of a path, but for now, it is possible to go by this edge. It is possible to go from 6 to 1, but not from 1 to 6. Okay, so every edge has a direction, or maybe it is better to say has a feasible direction. Okay, so far we know that every graph is undirected or directed. We can look at graphs from another perspective, the perspective of weights. These two graphs that I showed you, undirected and directed, there is nothing on the graph other than the edges and the vertices. Okay, but In some applications, we can also put some numbers in this graph. For example, we can associate every vertex with a number, say 1.2 for this one, 2.4, 61, 52, 1.9, and 2.3, something like this. So in this graph, in addition to the vertices and the edges, I have some extra numbers which are assigned to the vertices. Okay, so every vertex I in the set of vertices is associated with a weight which I denote by Wi. Okay, for example, in here W1 is 1.2, W2 is 2.4, and so on. A graph like this, where every vertex is associated with a weight, is called a vertex weighted graph. Okay, you can easily see that I can extend this weight, the concept of weights, to the edges, so I can define graphs where every edge is associated with a number, like this: 12, 15, 11, 2, 2.1, 1.9, and 0.6. Okay, and a graph like this is called an edge-weighted graph. These weights give some information about the edge. For example, if this is a graph that shows similarity among vertices, okay, then you can, like what I explained on the network of businesses, when you have a thicker edge, this means that the relation between these two is stronger than probably between the relation between these two. So you want to represent the strength of this relationship with a number. In a similarity graph like this, the edge weights represent the extent of similarity, for example. Another example, if this is a transportation graph, represent a transportation network, then these numbers on the edges can be the length of the distance between these two vertices. For example, if this is a transportation network of 6 different cities, then this can represent this number 12, for example, can mean that the distance between city 1 and city 2 is 12 miles, or from the city 5 and city 6 is 11 miles. Okay, so these weights, the vertex weights and edge weights, add additional information based on the application that is under study. So yes, as I said, so one categorization could be undirected versus directed graphs. The other is unweighted graphs versus weighted graphs. And as I said, when we talk about weighted graphs, then it is either vertex weighted or edge weighted or both. Okay, these are just some terminology. Okay, more definition. So far you know what is a graph, what is a vertex, what is an edge, also what is undirected graph, a directed graph, unweighted graph, and weighted graphs. Now I'm introducing a couple of more concepts. Let's talk about chain and path first. These two are very similar concepts, chain and path, and in most cases they are used interchangeably. Actually, if you want to be more rigorous, we should say that a chain is defined on directed graphs, And when we are talking about directed graphs, we prefer to use the term path. A sequence of arcs such that every arc has exactly one vertex in common with previous arc. Okay, this is the definition of chain. It simply means that if you have a graph, something like this is called a chain. It is a collection of arcs, a sequence of arcs. This is an edge. As I said, arc, edge, and link are the same things, okay? So this is an edge, this is the next edge, and these two have one endpoint in common. The next edge is this one, and it has this endpoint in common with previous edge, and so on. Something like this is called a chain. Okay, but when we talk about directed graphs, okay, remember that in a directed graph, we can easily think about walking on a directed graph, right? It is very intuitive. So if I have in a directed graph, we will have a path if it is possible to walk through the edges according to the directions. Okay, so this is a path from A to B. But in case that I have something, in case that I have something like this, okay, this is not a path from A to B, because it is impossible to go from A to B through this path. You can go from A to this point I, for example, but you cannot go from I to J, and consequently you cannot go from A to B. So this is not a path. But in the original graph, this one, it is indeed a path. Okay, the sequence of the edges is a path from A to B. More formally, a path is a chain. Of course, is a chain because in definition of a chain we didn't talk about direction. We just said that it is a sequence of edges. Every edge has exactly one vertex in common with the previous edge. Okay, in here, in addition to that, we also include the directions in the definition. Okay, so a path is a chain in which the terminal node of each arc, okay, remember every arc starts, every edge in a directed graph starts from a vertex and ends in a vertex. Okay, so this is the start, this is the end, and it says that the terminal node, which means that the end node of this edge is exactly the start node of the next edge in the sequence. Okay, so this is about chain and paths. The other concept that we have is cycle. It is again intuitive. We have cycles in undirected graph as well as directed graphs, and a cycle is simply a chain in undirected graph. A cycle is a chain such that the start vertex, the both end points of the chain are the same vertex. Okay, so this is a chain, and if it happens that this chain has another edge which connects this vertex I to the start vertex, then I will have a cycle. Okay, you can easily think of directed graphs where you have something like this, right? So a cycle is a path or a chain with an extra edge that connects the last vertex to the first vertex. Another definition, a connected graph. Okay, again, it is very intuitive. A connected graph is a graph that between every two vertices there is a path, which means that you can go from every vertex to every other vertex. Okay? So consider a graph like this. Obviously this graph is connected because every two vertices that you give me, I can show you that there is a path between or there is a chain, there is a path between those two. Okay, for example, between this one and this one, I can follow this path. Remember that I told you that when you have an undirected graph, you can think of those edges as bidirectional edges. Okay, I can go this way or this way. Both are possible. Okay, so if you have a graph like this, that there exists a path between every two vertices, then you have a connected graph. Example of disconnected graphs, very simple. This is a disconnected graph. Okay, I'm not showing you two separate graphs. No, this is a single graph. Okay, so this graph, this is G. So 1, 2, 3, 4, 5, and 6. So the set of vertices is 1, 2, 3, 4, 5, and 6. And the set of edges, this is how we show, we represent the set of edges. E, as I said, is the set of edges. And 1, 2, 2, 3, 4, 6, 5, 6, and 4, 5. Okay, so this green graph is a single graph, but it is disconnected because, for example, there is no path between 2 and 4. Right? Technically, we say that this part is a connected component, this part is another connected component of G. So G has two connected components, but these two are not connected to each other. Okay. Before I go forward, let me add something about this notation. Of course, as I said, that V is the set of vertices, so it's a natural way to represent a set. Okay, 1, 2, 3, 4, 5, 6. Now about the edges. This notation that I use, for example, I said 1, 2. Okay, this is an ordered pair. Right? It means that this element, let me use another edge. For example, the edge 4, 6. It's an ordered pair. This notation that I put them in parentheses means that it is ordered, which means that this comes first and this comes second. So this notation is more appropriate for directed graphs, right? So when I have a graph like this, 1, 2, 3, then V is 1, 2, 3, and E is 1 and 2. Which simply means the edge starts from 1 and ends at 2, and 2, 3, right? So this is a proper notation when we talk about directed graphs, but when we talk about undirected graphs, actually it doesn't matter which one, something like this. It doesn't matter which one is first, which one is second, right? Because all this thing tells us is that there is an edge between 1 and 2. So if you want to add direction to it, it means that it is both 1, 2 and 2, 1. So a more appropriate notation for this, in this case, is to use a set notation. So again, V is 1, 2, 3, and E, it is better not to use this parentheses that we used here, because it means that it is ordered. We want to emphasize that it is not ordered. So it is better to again use the set notation and say 1, 2 is an edge and 2, 3 is an edge. Okay, so this is a more appropriate notation to use for undirected graphs, and this is a more appropriate notation. It is actually the correct notation for directed graphs. But let's say we know if our graph is directed or undirected, and just for simplicity we will use this notation. We will use parentheses, okay, just for simplicity. Okay, we define what is a connected graph. As I said, the definition is very intuitive. If everything is connected to other things, then it's a connected graph, otherwise it is disconnected. Now the last piece of definition that I have here is the concept of tree and forest. In graph theory, a tree is a connected graph that has no cycle. Okay, so consider this thing, for example. This is a tree. Okay, why? Because I cannot find any cycle in this graph. Remember, a cycle is something like this. Okay, so there is no cycle in this graph. There is no cycle in this graph, so we say that it is a tree. Okay, but if I add an edge, for example, this one, then it is no longer a tree. Why? Because then I will have this cycle. Okay, by adding this edge, this tree became not tree. So this is a definition of a tree. A tree is a connected graph with no cycle. Okay, if you have a cycle in your graph, then your graph is not a tree. We also have this thing that a tree is required to be connected. So let's go back to the original tree. This is a tree. Okay, if I add these 3 vertices to my graph, again the entire thing is a single graph, but it is no longer connected, right? This part, this connected component is a tree, this connected component is a tree, but the entire thing is not a tree. Okay, in this case we call it a forest. Okay, so a forest is a collection of trees, as it is in nature. Okay, so a tree is a connected graph with no cycle, and a forest is a collection of trees.
Talking trees. What do trees have to talk about, Except the consistency of squirrel droppings.